When a system is overloaded, at some point the system crosses over into nonlinear behavior. It can crash, thrash, stop responding, or break adjacent resources that the service depends on. There's a very specific relationship between failure due to loss and failure due to overload. Imagine, for example, that a resource is lost and you queue up the work for that resource. All the work that comes in gets backlogged. When the resource is restored, there's this tremendous backlog of work to get done before any new work can be handled. And if there's enough of it, nothing new ever gets done. So then the system goes from being totally unavailable due to resource loss to totally unavailable due to overload. In this lesson, you'll learn about the common causes of overload failure and how to plan for them and deal with them. When it comes to overload, prevention is really the best solution, so design is critical.
So here's some common behaviors, right? Failure due to overload. Now this occurs when a resource crosses into a nonlinear behavior, running out of memory, running out of disk, which we call thrashing the disk. It can stop responding. There's no network available. There's no memory available. The CPU is too high. What will happen? It creates this huge chain of effect, and all the services that depend on it can fail. So let's start with kind of an overall networking service architecture. So here you're load balancing, and you've determined that your front ends can handle a maximum of 1,000 QPS. So you'll notice that you've designed the network to handle for that kind of QPS workload. Your front end clusters, here you can see we're evenly distributed. We're at about 900 QPS, so that's pretty good, but pretty close, because imagine if one of these fail, right? Or a failure domain, we lose this load balancing. That means all our requests will have to happen over here. And of course, we would lose our failover backup links, and all of the traffic from here would then have to be handled by the front end A. And so what about growth? Well, again, in this case here, if we were to double that, could we still handle the additional QPS? So you want to think about not just from a failover, but for growth reasons as well. Now, cascading failures. See, what could happen here is if our front end can only handle 1,000 QPS and we're already sending 600 to multiple front ends. If one of those goes down, now you've overloaded front end A, and here's a huge list of cascading failures that can certainly occur. Now, it can be very difficult to try to troubleshoot when you have all of these independent alarms. This is why you kind of have to identify, in the beginning, what should be some of the first things that happen. This is why log data is going to be important. What was the first thing to alarm? And especially when we talk about how we monitor both black and white box. So monitoring the individual services, but also from the user experience, which might help give us additional clues. So designing to prevent cascading failures, and this is extremely important. So this is where prevention is kind of the best strategy. It can be very difficult to roll this back. So we really want to monitor safety size. So notice that we want to make sure our CPUs don't exceed too much, and we want to auto scale a little bit earlier just to kind of keep ahead, because what is the cost of downtime versus the cost of adding more servers to kind of absorb the short-term or even longer-term traffic load? So we want to increase the size of our clusters for failover, not just for operating capacity. Remember, N+2 to handle for failover, but also adding additional so we can handle growth. So let's think about this. So here we're creating, say, distributed backends, and that's fine. So you have a server requesting from the backend. But what happens if it's auto scaling it's distributing and load balanced across multiple backends, and they all want to respond? Well, guess what? Then that server can become the single bottleneck. So you want to identify any type of fan-in or incast overload failures to where you may get a flood of responses from these clustered systems, which we'll actually probably find when we get to our photo service. If you remember, we scaled the backend thumbnail servers, but what about the front end, which is going to be handling a lot of the responses? That still could be a fan-in or an incast bottleneck. So what we decided to do, and what you'll see at Google, in fact, if you look up some white papers on how BigQuery is designed, you'll see this kind of tree architecture in which we keep redistributing to clusters of nodes through different tiers, different leaf nodes. And from this, it really can solve a lot of problems. So it limits the single server fan-in because you're responding back. You don't have exactly one node distributing to every single leaf in that node. And of course, they can respond to many nodes. And the nodes combine data from children and aggregate it, and so this way they can continuously filter before they send the results back to the front end. Another one is the queries of death overload failure, in which you can get kind of like these feedback loops. And so this basically occurs when business logic errors show up as overconsumption of resources and the service is overloaded. So you run this query, there's no resources left, and so the query tries to retry, and so you get kind of into this feedback loop. So here's our little example of a feedback loop, right? You're trying to make the system more reliable by adding retries, but instead you create the potential for an overload. So there is a fine balance between how often you retry and how much you back off. So like a logarithmic back off might be something. So this way, if, for example, it doesn't respond after the first minute, you make it 3 minutes. And if it's not 3, then it might be 10, and it starts to really, back off how often that it retries. A good example is if you take a look on the internet and do a Google search for route dampening. BGP has designed this since the early days when you were announcing network routes. If your interface kept going up and down and all of a sudden you had to rebuild your route table, people would just simply ignore you, right? And it was called route dampening. I think that's a really good concept that you can apply to a lot of health checks and retries. Another way to detect overload is early warning systems, or canaries. So in this one example is where we launch and we test a single server before enabling auto-scaling on an instance group. We want to test that server to see how well its workload is, and then what we might do is limit the size of the auto-scaling group, because if you had a feedback loop, and imagine you could quickly maximize the max setting on your cluster size. So let's go ahead and keep it small. That's when you monitor it before you let the systems kind of rule themselves.